A critical point when deploying redundancy is that while on the one hand, reliability math lets you assume only one component fails at a time, on the other hand, you also need to ensure that all the components are working perfectly at the start of a mission. That means you need to be able to find and eliminate any latent faults before the mission starts. One way to find latent faults is with online diagnostics such as a self-test at the start of the mission or continual background checks while the system is operating. While these cannot find all faults, they are certainly important for safety-critical systems. Creating a thorough self-test can be very challenging, so you should use a vendor-supplied library such as IEC 6730 self-tests if you can. Another way to improve diagnostic coverage is by using a thing called a proof test. It's called a proof test because the purpose of the test is to prove that the redundancy or safety function is still working properly. Let's use an elevator safety limit switch as an example to motivate why you would want a proof test. If you have been to a shopping mall or an airport that has an open-air glass-enclosed elevator, you might have looked into the enclosure to the top and seen something that looks like this. The bottom right of the picture shows the top of the elevator car frame going from the middle bottom of the picture up to the middle right of the picture. The elevator has a guide rail that keeps it from jiggling around and swinging in the hoistway, and there are guide wheels to follow that rail as the elevator moves up. However, at some point, the guide rail has to end, and it would be very bad if the elevator just popped off the end of that guide rail. The way you know the elevator won't pop off the end of the rail is that there is a metal bar attached to the car frame that hits position switches as the elevator moves. In normal operation, this bar, which is now highlighted in yellow, shoves the top floor position switch to one side, causing the computer to stop the elevator at that top floor. However, that switch will eventually break, and we want to have redundancy to avoid overrunning the top floor. There's an overrun safety switch to detect when the elevator has gone past the top floor and is about to run off the end of the rail. This switch is just there in case the top floor switch fails. Well, that sounds great, but how do you know that the overrun safety switch is actually working? It should never be exercised when the elevator works, so you have no idea in normal operation whether that switch works because it's never supposed to be actuated. The answer to this is use a proof test to intentionally overrun the top floor and activate that switch. This can be done every once in a while by an elevator mechanic running the elevator very slowly in a manual safety mode just to make sure that switch is tested. Testing that switch is a proof test to prove that it still works. This is a general concept and needs to be applied periodically to any redundancy to make sure the redundancy is still there and still working. That includes sensors, actuators, and redundant computational elements. What proof tests are really getting at is looking for latent undetected faults, which are faults in the redundancy that you cannot tell are there because normal functionality masks the failure in the redundancy. For 2 of 2 systems, the worry is that a fault will happen in one of the 2 channels, it will be missed, and the other channel will accumulate the same fault sometime later. For any redundancy, you want to do online detection that includes frequent cross-checks not only of system outputs, but also of the internal state of the system to make sure that no bits that are used very seldom get corrupted in a way that is unnoticed. You also want to swap active units in a primary standby pair. That way, each of the pair gets a chance to be the lead unit and gets exercised in normal use. Finally, you need to do periodic offline detection by enforcing proof tests that can consist both of extensive self-tests and human-assisted diagnostics.